So in today's lecture, we'll cover following two topics. First, we'll discuss about deflection by work energy method. Yeah, this will be, I would say, the real meat of this chapter, energy method. So finally, we can taste the real meat today. After we talk about work energy method, we'll discuss about extension of work energy method for more complex loading with multiple load problems. Okay, the typical sequence that this textbook used. This textbook always start with the simplest possible example with a single load. After we understand the single load problem, the textbook then try to extend the concepts to multiple load or complex loading problems. Okay, so we'll just follow the logic of these authors in chapter on energy method too. Okay, so let's begin from the work energy method. So let's discuss about simplest possible problem to explain what work energy method and the equivalence between work and energy. Actually, even though I give a fancy name here, you already know the work energy method from freshman physics. For example, if you try to compress a spring, you're gonna you should do some sort of work done, which is one half final force multiplied by final displacement, and that force is stored as potential energy within the spring, right? And the work done and the strain energy stored in the spring should be equal to each other. Okay, so here we're gonna do exactly the same way. So we're gonna consider relatively, I would say, almost quasi-static loading, so that you don't have any like a huge acceleration or dynamic effect or energy loss from the noise or energy loss from friction. You don't have any energy loss. If there is no energy loss, and if you consider quasi-static loading, you can say for sure that work done is equal to energy stored. Okay, so let's do that. So let's first consider this simple cantilever beam bending problem. From the appendix, we already know the relationship between the applied force P and the displacement at the right end. Okay, so you can find this from the appendix table that we discussed back in statically indeterminate beam deflection problems in previous lectures. So let's first consider work done. So what you can imagine here is that when you start deform the beam, in the initial stage of the beam deflection, you don't need like a large force, right? The force and the deflection has linear relationship, right? Ym is proportional to P, and this proportionality constant is given as in terms of the geometric parameter, material property, and cross-sectional area, right? So if you write down the relationship between applied force P and the displacement y, it will show this linear relationship, right? The force and deflection will be proportional to each other, and what you can see here is the area below this triangle corresponds to work done at the end of the beam. Okay, and at this final stage, ym is given as p l cube or 3ei, and if you obtain this area behind this below this force displacement curve is 1/2 p times ym, and it's given as p square l cube and divided by 6ei. Okay, now let's check if this work done is the same as strain energy stored for entire body. And actually, if you recall in what we have done back in previous class, we considered like an integral over m square over 2ei dv. If you perform this integration over the entire body, you may remember that the answer is the same, like a p square l cube divided by 6ei. Okay, so what you can see here is when we obtain this thing, without relying on any expression for strain energy, we can obtain the relationship between ym and p Okay, and from this relationship and the work done at the end of the beam, only at the end of the beam, we can obtain the work, and this work, happen to be exactly same as the strain energy, you know, obtained by integrating strain energy density over the entire volume. And what you can see here is, if we consider the ideal quasi-static loading without any energy loss, such as like a heat or noise and other form of energy loss. And in this case, because we didn't consider any of them in our ME231 course, the work done should be same as strain energy saved for entire body. Okay, so this is from energy conservation principle, which is trivial, right? And we can do the same thing for the pure bending. And from the appendix of beam deflection chapter, the relationship between applied moment m at the end and the angle theta has this relationship. Theta is proportional to m, and the proportionality constant is L over EI. So if we obtain the work done from theta and m diagram, and by obtaining 1/2 of m theta, it turns out to be m square L 2 EI. This is the work done obtained from half torque times angle. Now, if you consider strain energy stored for the entire beam, this beam under the pure bending, and if you perform this integral over the entire body, as you expected, you found that strain energy stored calculated from integral of strain energy density turns out to be same as work done at the end of the beam. Okay, so this is so-called like the equivalence between work and energy, and using this work energy equivalence, you can obtain the deflection due to a force applied on or loading applied on some point of the structure. Okay, so let's solve like one example problem. This problem we consider relatively short, and no, I cannot say it's short. Let a cantilever beam with small aspect ratios, that would be more appropriate expression. So when we consider like a cantilever beam with relatively small aspect ratio less than 10, here the implication is that we cannot use the Euler-Bernoulli beam theory. Okay, and suppose that somebody give a force P at the end of the beam, and the problem asks us, can we obtain the deflection at the end of the beam at given force P? So first thing we have to realize is we can't use Euler-Bernoulli beam theory because the aspect ratio is small. So for this small aspect ratio, we cannot use Euler-Bernoulli beam theory. We have to use work energy method. So if we consider work done, okay, so at least for this problem we don't have any known solution. So let's say that because this is a linear problem, P and Y should satisfy proportionality relationship or linear relationship, but at the end of the deflection we don't know the exact relationship between P and Y. Okay, so we can just write down that work done is given as 1/2 P times Ym, and Ym is of course unknown value. Now let's consider strain energy. So for the strain energy, what we can do is out of this problem, we can obtain distribution of V, distribution of M, and out of V and out of M, which generates shear stress, which generates normal stress, we can obtain U sigma and U tau. And in previous lecture we found that the strain energy can be written as this way. Okay, P square L cube over 6EI multiplied by 1 plus this correction term, and the correction term comes out of from this tau term. Okay, so after realizing that we have obtained the expression for work W, we have expression for the strain energy U, okay, both in terms of P and other geometric and material properties. The only one unknown is Ym. So from the energy conservation principle, what you can do is we can consider this equality equation, and we can obtain the expression for Ym. So what you can realize here is that if this guy is 0, it becomes identical to the simple problem we considered in previous page where L over D is very large case. Okay, however, when this L over D is not large, if the aspect ratio is not large enough, in addition to this term, we have more additive correction term. Yeah, this additive correction term comes from the effect of the shear force in Euler-Bernoulli beam theory. When we obtain this expression, we don't consider any contribution from shear stress and shear strain. However, here by exactly considering the contribution of shear stress and thus shear strain, yeah, we have additional deflection. Okay, so this is the exact expression for beam deflection considering this simple cantilever beam bending problem with relatively small aspect ratio. Okay, so yeah, this is a typical use of the work energy method. And actually, if I give you more general application of this method, yeah, I can introduce in this way. As I told you, even for this beam deflection problem on the point of force, we know that like the P and Y, the deflection and force should be linear to each other. When force is 0, deflection would be 0. When force becomes like a twice larger, and the deflection will be twice larger from this linear elastic problems we consider in ME231. Okay, so we can just say that y is some unknown alpha multiplied by p, and we can write down work as half alpha p square from the yeah the from the area below this triangle, and this work done should be same as strain energy stored in entire beam, and this strain energy can be obtained from moment diagram or shear force diagram or other diagram. And what you can realize is that because half alpha p square must be same as up, if you consider partial p and partial p both left and right side, left side becomes alpha p, right side becomes partial u and partial p, and alpha p is defined as y. So y, the deflection, can be obtained from partial u and partial p. Okay, so if you have the expression for potential energy in terms of applied force at at some point, and if you do partial u and partial p operation, then you can obtain the deflection at that point along the direction of the force. Okay, so this is what this derivative relationship implies. And actually we can do same thing for the point bending and point torque problem. So for point bending problem, yeah, here we already know that theta and m, they are linearly proportional to each other, and the beta is, suppose that beta is unknown, so w can be written as half beta m squared from the triangle, and it should be same as the strain energy stored for entire beam. So if you do partial m and partial m for both left and right side of the equation, yeah, you found that partial u partial m should be same as beta m, and beta m is defined as theta, so theta can be written as partial u and partial m. Or in other words, if you have the strain energy for the structure as a function of m, you can obtain theta from this partial derivative. And we can do same thing for the point torque. If you consider torque applied at at the end of the bar or some middle point of the bar, whatever point it is, the relationship between twist angle and torsion T can be written as in this way, and suppose that gamma is some unknown proportionally constant, and of course W is written as half gamma T square, and it should be same as strain energy stored for entire beam. And of course by doing same operation, partial T for left side and partial T for right side, yeah, you can find that from partial u partial t you can obtain the angle. So even whether you consider the dimension of force, whether you consider dimension of torque and dimension of torque, you can apply this work energy method and this partial derivative method for solving deflection or the angle along the applied loading method. Okay, I mean applied single external load. Okay, so and you don't need to worry about the dimension. Okay, so if you do partial derivative over force, you're gonna get deflection. If you do partial derivative over the torque dimension, you're gonna get angle along that torque direction. Okay, so this is the implication and the principle of work energy method. Okay, so let's solve one more example problem. So here we consider a triangular structure. So this is rigid wall and rigid support, and you have the distance between C and A point with L, and the distance between C and B, two force member, is 0.6 L, and the distance between A and B, another two force member, is given as 0.8 L. So you can see that this is typical 6, 8, 10 ratio, which means that we can get easier solution by using the Pythagoras theorem. Okay, so this problem asks, when somebody apply a vertical force P at the at point B, what will be the deflection at B point? The problem asks this question, and at the end point, by considering the force equilibrium in horizontal direction and vertical direction, we can obtain FBC, the tension along BC component, and FAB, the tension or compression along AB component, in terms of P. Okay, so the reason why we convert the internal force in terms of P is that we want to obtain U as a function of P, and after obtaining U as a function of P, if you do partial U and partial P, you can obtain deflection at B point. Okay, so that's the strategy we are using. So FB and FBC and FAB, both of them are unknown. If you rewrite those unknowns in terms of P, which is a given value from the problem, you can write down the potential energy in terms of P, and out of this expression you can obtain deflection. So let's plug in the value of FBC 0.6p and 0.8p, value of FAB in the expression of strain energy. So strain energy expression for BC, strain energy expression for AB can be written as this, and both FBC and FBA is a simple constant, 0.6p, 0.8p, and you do this integration over entire length, which is 0.L and 0.8. After plugging in all those expressions, what you're gonna get is P square L over 2EI, and you have 0.6 cube plus 0.8 cube. Okay, so you have 0.8 here, you have 0.8p here, you have 0.6p here. So that's why you have 0.6 twice power and another power here. So this is why you have a cube here. Anyway, after making this operation divided by 2, you're going to end up having 0.364 p square over L over AE as the strain energy stored in the entire structure. Here, what you can see here is this this support and that support, and these residual, because they are rigid part of the structure, so you don't expect any strain energy storage over this side. Strain energy is stored only within here. Okay, anyway, so after obtaining U as a function of P, we can do partial differentiation, partial U and partial Q, and this will indicate the deflection at B along the direction of the P. So it will be given as 0.728 PL over E. Of course, instead of using this partial U and partial P, you can consider half P YB equals to be U, and if you obtain YB by removing P over 2 to right hand side, you'll be obtain the exactly same answer. Okay, so this is the final example problem considering just one unloading problem, and we can ask like a further questions as an extension of this. First question I can ask is, what will be the how to handle the multi-loading case. Like here, instead of the single loading, we can have a point force, or we can have additional point moment. Then we can write down U as a function of P and M. Then can we obtain Y in terms of partial U, partial P? Can you obtain theta in terms of partial U and partial M, even though U is a function of both P and M. And the second question you can ask is without any point loading. For example, until now we keep considering like a point force and point bending and point torsion. If we have only distributed loading, can we obtain like deflection at D point from work energy method, even though there is no point force? If there is no point force, can we define some sort of force P that can do like partial U and partial P? What will be the method? Okay, so yeah, we'll discuss about these two questions. So for the first question, yeah, we'll discuss a little bit today, and further discussion will be delayed to next lecture. Regarding the second question, yeah, we'll consider this question in the next lecture. Okay, so I will stop the recording of the first part of today's lecture here, and let's continue regarding the multiple loading problem in the next video.